Okay, hello everyone, here we are again with an energetics type question, and today we're going to introduce Hess's law and then use Hess's law to help calculate an enthalpy change for the reaction shown, and also from that show how we end up with a rather useful formula that will help us to find enthalpies of reaction if we're given enthalpies of formation. In this case we are. Well, Hess's law states that if you have a chemical reaction, the enthalpy change that goes along with that reaction or accompanies that reaction is independent by the way the reaction takes place, as long as the initial and final conditions are the same. So that, in other words, that means if we've got a chemical reaction, the energy change given out or taken in with that reaction is the same however you get from the reactants to the products. So that's really useful for helping us find out enthalpy changes for really difficult experiments to do in a lab, for reactions which it's really difficult to find the enthalpy change. Now for the one we've got up here, it's enthalpy of combustion. We can do that in the lab quite easily, but it's a good example to show us how Hess's law is going to work here. So I'm going to start by writing out my equation. We've got ethene, C2H4, and it's burning with 3 oxygens to produce 2 carbon dioxide and 2 molecules of water. I'm not going to bother to include the state symbols this time. So we're trying to find this enthalpy change. I'm just going to call it an enthalpy change for reaction, but to be more specific for this case, it's an enthalpy change of combustion. Well, Hess's law says that energy change, delta HR, is independent of how we get from the ethene and oxygen to the carbon dioxide and the water. So if we try and create a cycle which includes all of the elements in the reactants and products, then we end up with what we call a Hess cycle. Now, we're provided with the enthalpies of formation. If you remember what the enthalpy of formation is, it's forming 1 mole of the substance from its elements in their standard states. So if we look at ethene, we're given the enthalpy change of ethene. Ethene is made from carbon and hydrogen in their standard states. So if we have 2 carbons and 2 hydrogens, that equation here represents the enthalpy of formation of ethene. So the energy change is delta HF for ethene. The enthalpy change of formation of oxygen is just coming from oxygen. There's no change, it's 0. Producing water just involves reacting 2 molecules of hydrogen and 1 molecule of oxygen. So this change producing the water is twice the enthalpy change of formation of water. Twice because we've got 2 molecules of water being produced. And the carbon dioxide, 2 molecules of carbon dioxide have been produced from 2 carbons and another 1 of the oxygens. Let's make that 3 now to make it all balanced. So this enthalpy change here is the enthalpy change of formation of carbon dioxide. However, actually there are 2 of them. So we've formed a Hess cycle. Admittedly it's rather messy, but let's see if we can if we use a red pen now, we'll see what we're doing. So Hess's law says that the enthalpy change accompanying a chemical reaction, and that's the one we're looking at, is just the same as if we go this way to if we go from here to here and then from here to here. So by Hess's law, we can say that this enthalpy change, delta HR, is equal to this enthalpy change here, but we're going back against an arrow this time. We're going in this direction against the arrowhead, so it's minus the enthalpy change of formation of ethene. We're also going back this way, but that's 0, so I'm not going to include it. Then we're going along this arrow here in the same direction as the arrow, so we have plus 2 delta H formation carbon dioxide, and we're also going in this direction along the arrow, so we're adding 2 enthalpy change of formation of the water. So I've now got myself an equation with values I can use. Minus the enthalpy change of formation of ethene is up here, it's 52, plus from here twice the enthalpy change of formation of carbon dioxide, so twice minus 393, plus twice the enthalpy change of formation of water, which is given here, so that's plus twice negative 286. If I solve, I end up with negative 1410 kilojoules per mole for my enthalpy change. I'd stop and pause and go through that now. Now, if you have a look at the enthalpy change and the Hess cycle we just looked at, you can deduce from that that for any chemical reaction, if you know the enthalpy changes of formation of the products and the reactants, then if you take the sum, using the capital Greek sigma here, the sum of the enthalpy changes of formation of the products, and you subtract from them a sum of the enthalpy change of formation of the reactants, you'll end up with the correct answer. A wonderful little formula you'll use lots, only if you have enthalpies of formation. Thank you.